Hello, everyone. If you are a software engineer or even a computer science graduate, you would have definitely heard or used the term caching. What exactly is caching? And are you using caching in a right way? I observe that many people use only one of the access patterns of the caching. That's the fallback mechanism. That's they will make the request to the cache. If there is data available in the cache, they will get the data. Otherwise, they will make the call to the actual data source or the database and get the data from there. But is that the only access pattern available? Or what are the common popular access patterns which are there, which will help you design your system in a way that it becomes fast and you get data in a very fast manner? And also the flow is smooth. And how exactly you cache your data? So let's quickly get started with various approaches, what all things we can do. Now, if we look into the common access pattern, and this is a scenario which we are going to talk about, that you have a backend and you have a front end and you have a database. Very common access pattern. This is being used many places. So we'll use it here as well so that we understand the problem. So we have a front end or a user. That person is trying to make an API call that, hey, I want to get a data for a particular sale. So imagine you have a backend with a e-commerce platform where you sell multiple things. You can sell Apple oranges, you can sell iPhones, you can sell mouse, keyboards, etc. So there is a customer and that customer wants to know that, hey, I have a invoice number X and I want to know the details of that payment or the sale which was done. I want to know the price at which I bought the item. I want to know lots of things. So I just want to know a bunch of things. I want to make an API call, get the data. The response body could be even better, but that's not the point. Imagine that you just want to get a response with a bunch of things. You make an API call, and this will be the ID of the sale. The request will go to the backend, and the backend servers, of course, is a stateless service. It does not contain any data, so it will make call to the database and get the data and give it to you. Now we'll talk about the problem statement. That in this scenario, what exactly we are trying to solve. Now, typically, how the data is stored in the backend. I'm not saying that this is how you would store the data, but there are many systems which are very much in the legacy state. The companies or the products which is started back in 2010 or 2009, they have a tendency to use relational database. And rightly so. There are many cases even today that you would be using relational database. Not just a relational database. Many times it happens that when the product started, it started in a way where you decided a particular schema for the database that, hey, I'm going to have a users table. This users table will contain all the users of my company. So for example, this is a user and this user's information like ID, name and email, I'll use store in a separate table. Then we have a different database for all the items in my company. So it could be, ID equal to 1 means iPhone with the price of 75,000. And ID equal to 2 can be a shampoo with a price of 100 rupees. And likewise, ID equal to 3 could be something else, maybe a Lenovo mouse of price 350 rupees. So all these things can come in the items table. And this is the sales table. That could be the third table in your database where you have user, item, and count. So user is a foreign key to the first table, and the item is a foreign key for the second table, and you have the count, that is the number of items you sold for a particular sale. So basically, the request will come for a user ID, and then you will take join between user table to get the information of the user. You need to get the information of the item because there are things related to the item, and you would need to get details of the sale because you need count as well. So count will come from the third table. The price will come from the second table. Item name will also come from the second table, and username and email will come from the first table. So typically you would have to take the join. Very common scenario. This is something which you would be doing in many of the cases. Nothing new here. Now you can see the problem. The problem is that maybe when the system was created and the people who created this system might have a very strong reason to go with this approach. But it might be possible that 10 years down the line or so, these tables grew to a very large scale. There are hundreds and thousands of users, there are hundreds and thousands of items, and you have lots of sales being done in your company. And now your APIs start to get slow. So now whenever a customer wants to get a sale for a particular ID, the moment you take join between these three tables and the moment you try to get the data, you get response very late. And it used to happen for one such product which I worked long back. So the same thing used to happen. The API response used to give us the data after 2.5 seconds. Imagine how bad the design was. It was not bad in the first place, but as and when the requirements come and as and when the product evolves, and there are so many people who worked for a product for around 10 years or 15 years, sometimes things don't fan out the way you want to. So the APIs became slow. How do you handle it? And how do you make the system efficient so that you no longer have the slow responses? So one such solution could be that, hey, I'm going to redesign my database. I am no longer going to have a relational database, and somebody came to you and said that, hey, for this scenario, relational DB doesn't work. I would want to use a document-based database or something else, and I'm going to migrate all my data to the new system. But that's not going to happen all of a sudden. It's not going to happen that I will shut down my system for 2-3 days and I will migrate all my data to the new system and then I'll serve the user from the new system. That's not going to happen. There will be approach using which you slowly migrate your data. So let's talk about that how do you handle the latency overall? So the first approach, the first and the simplest approach you could do is that you introduce the concept of caching. And that's a very common pattern that whenever a user makes a request, the request goes to the backend service. And the first thing you do is to check in the cache. And this cache could be anything. It could be a key value store like Redis. It could be anything else as well. Even Mongo you can use as a cache. That's not a problem, because what will happen is that you will make a request for a particular ID, that is sale ID 1. If you get the data, you will return from here. Otherwise, you will make the call to the database. You will take 2, 3, 4 joins, whatever join you want to take. And then you will construct the response JSON, and then you will save this response JSON here in the cache. So the next time, it's a just simple get and put operation. It could be even from Redis, it could be even from Mongo or Cassandra, doesn't matter. But the thing is that, imagine, let's consider the simplest case of Redis. We'll just have a key of sale underscore summary underscore 1. 1 is the ID. And the value will be the whole JSON. So the next time when the request comes, it's a simple get input operation. It is mostly fast compared to you querying 3 different tables. That's the simplest approach which you could do. The problem is that it does not fully solve the problem, because what can happen is that the first API will still be slow. The first call which you make, it will be a cache miss. And then you will make the database call, you will get the data. And from the second API onwards, you will be fast. But the first API is going to be slow. And yeah, you could end up in a scenario where your database can go down, and your database is supposed to be sacred. It should not go down because of lots of requests. So what will happen is that during the peak hours, if there are many people who want to get the data about their sale, all the requests will go to the database because the cache miss will happen and your system can go down. So it solves a problem to a certain extent, but it does not fully solve the problem. So that's the first approach, and I hope this would be creating a mind map for you that how the approach would work. That's a simplest approach. This is where you are doing the orchestration, the call 1 to cache and the call 2 to DB and call 3 again to the cache. So that's the first approach which you can take. Now let's consider the second approach. In the second approach, I'm not going to have the fallback logic. I'm not going to have 3 calls. That's the first call to the cache and the second call to the database and the third call to the cache, because it was not solving all the problems. So what I'm going to do is that I'm going to pre-compute all the responses for the request which user is going to make. That is, let's say somebody does a write operation in the database. I'll write some code or I'll do something so that my responses are pre-computed. So here, even if my database has 3 tables, 4 tables, 5 tables, doesn't matter. And even if I have to take 3, 4, 5 joins together to get a data, what I'll do is that the moment a write operation is done on the database, I'll do something so that a pre-computation of the response is done. Basically, a flattening of the data is done. Flattening means that whenever a request comes, I'll just give the pre-computed response. I will not even have a fallback logic. I'll know from before that the data is going to be there in the read operation. Imagine a write operation is done, and let's say after a second, 1 second, a user makes a read operation. Let's say a user completes their payment. So the payment is done, and within, let's say, 1 second, the user makes a /slave/id call, and the request will land here. And the request is guaranteed to be served from here. That's what we are going to do. We are going to have a pre-computed responses. So how it is going to help is that, first of all, now we have at least made the read operation fast. That is that instead of taking the joins at the runtime, what we are going to do is that we have a pre-computed response and the user will make the request. So this is going to be fast. And yeah, overall, there are two approaches in which you could pre-compute the response. So that's the important part. And some people use one and the other people use other. So it's important to understand this kind of caching logic. So the first thing which you could do, and this is what is preferred also. So this approach you should try first. And if it doesn't work, then only go to the second approach. So how do you pre-compute the responses? The first thing is you could do is that you use whatever is provided by the database itself. So many of the databases have a concept of materialized view. Now, if you use this materialized view concept, then it will be just the matter of writing some query on the database. The moment you write some queries on the database, you will have a pre-computed data in the database itself, which means that you no longer have to query the actual joins, etc. You just query the particular pre-computed response in the database and you will get the data from here. So there is no fresh deployment needed. You don't have to take any approval or any compliance review, etc. within your company. You don't have to write a separate code. You don't have to do anything. You just have to write some query. So the query looks something like this, that create materialized view. I'm talking about the query in Postgres. The similar query is there in other databases as well. So this is the query which you are going to write, create materialized view with some name. Then you will write the query, and then what will happen is that database will pre-compute everything. And after certain duration, let's say after a minute or so, you keep on refreshing the view. So in this way, you will keep on getting the new data to your views. This is how you can get your things done, and then you can query from the materialized view directly. So the advantage here is that you don't have to do anything except for writing this query, and then everything will be taken care by the database. It has been tested by many people and you can use it. I will just show you the demo or how it is done in Postgres so that you have some idea how it is done. So what I have here is a Postgres database. You can check out how to install Postgres database. It's not very hard. But what I'm going to do is to showcase you what exactly and how exactly things are done here. First of all, I'll clean up my things. So my views are clear. Now here, the first thing I'm going to have is a user table. So basically what I'm going to do is that I'm going to have 3 tables. And at the runtime, I would need to take join between 3 tables. So first is the user table, as I earlier talked about. Second is item table, and the third is sale table. So these are the 3 tables which I would need for my things. So I'll just run it so that my tables are created. Again, creating table is something which you can search online how tables are created, and you can see the first table has something, second table has something, and the third table actually has a foreign key to the first and the second one. So overall, the thing is that the data which I need requires the join from the 3 tables. So I'll insert some values to my tables. So that's also simple. Insert query. You can again check out how to run insert query. So I have 2 users in my company, Anubhav and Arjun, and they have their email address. Likewise, I have 3 items in my company, iPad, shampoo, and gym gloves. And whenever a sale happens, I add 1 row to my sale table. So it will have a user ID equal to, let's say, 1, which would be auto-generated, bought an item ID equal to 1, and the count is 1. So likewise, I can have multiple users and multiple items being bought, and each sale generates 1 row. So, but this table does not contain enough information anyway, right? So if you return to the front end 111, it doesn't make any sense. So of course you will have to take joins and then return the data. So I'll run the third query and it inserted a bunch of things. Now if I run this query, select from all the three tables, you can see that the first table returns 2 users in the company. The second table is around the items in my company, iPad, shampoo, and gloves. And the third one is the sale. So the first one is the sale ID, the second is user ID, item ID, and the count. So I could return the responses based on this particular data. Now, whenever somebody makes a call that, hey, can you give me the data of a particular sale ID? What I need to do? I need to run this query, select from, taking 2 joins overall. So the moment I do this, I can get data which I can send to the front end. So this works fine. Now the problem is that at runtime, taking joins between 3 tables is expensive. And at times it could be slow and it can have impact on the database as we talked earlier. So what we can do is that we can pre-compute things. So for that, what I need to do is that I just need to run this command, that is create materialized view. What it will do is that it will pre-compute stuff so that you don't have to do things at the runtime. Now, the moment I run this, it will create a materialized view with no data. Now, in the first place, I cannot do anything. I first have to load the data to my materialized view. So I have to run this command. Again, it's all syntactical and I think it deserves a separate video and you can find the people online, but I'm just going to give you the overall overview of the topic. So I'll run this thing, which will actually load some data to our view. And now I can query from the view directly. So if I run this, I can get the data that sale with ID 1. If I could actually comment the remaining part, that is, I can choose not to query on the ID and still I would be able to get the data. So let's say I query here and I'll get all the data. So this one will be faster. You could even test out and check on various online forums why it is faster. But overall, the thing is that database will do the work for you. You don't have to do anything. So it will flatten the data in a way that now you are making the simple query. The thing is, it will happen in the background. So whenever you run this command refresh, at that time, this particular thing will happen. Now imagine you have one new sale. The moment you have one new sale, it will not be reflected in the sale summary. The sale summary will still give you the old data. That is, it will still give you 3 records. It's not going to give you 4 records because there have been 4 sales. So for that, you have to refresh your view. So you have to periodically run this refresh view, or you could have various smartness around this. But the moment you run this refresh and then you query the sale summary, now you will get 4 records. That's the, one more sale got added. So in this way, just by writing a few queries to the database, you could just handle the pre-computation logic. Here, the important thing to keep in mind, and I'll request you to check out further as well, that it could happen. What happens is that when you run this materialized view, it takes table lock, which would be not a thing which you would want to. So for that, they have started to support something called as concurrently. So basically that allows, I think from Postgres 9 or 10 something, they started to allow concurrently. That means that it will not take any lock. So I'll paste all these commands in a GitHub repo and share with you, but you get the idea that without any fresh deployment, without any having CI/CD pipeline, anything, you just run some commands on the database and you are done. So you will have all those performance. But many times this will not be possible. And that's why I wish to talk about the other approach. So what happens is that although I have drawn a database here, but many times these databases are owned by different teams in your company. And it just gets hard for you to run some things in the database. And also sometimes you need to take care of the compute resources that, hey, view thing is not at all possible for me. And there will be many such scenarios in which, the compute resources is one such thing. Ownership of the data with a different team is another thing. So in those cases, you cannot alter the data. You cannot run the materialized view. In such cases, what do you do? So in such cases, this is also a very common scenario. And we used that scenario, I think around 6-7 years back. And that was wonderful because in our case also, the database was a legacy database. It was a database which was being used since the beginning of the company. So what was happening is that there were lots of joins and lots of normalizations, things which were very much popular back in 2005 and 6. So we even had queries and stored procs of the length of 1500 to 2000 lines. So these many joins were being taken in the database. So of course, these APIs were slow. So what we did was that the moment a write operation happens, we wrote some Java code, and that Java code used to poll the database every 2-3 seconds to figure out what are the new rows which are added to the database. And then based on the whatever the rows which are added, it used to pre-compute the joins that, hey, let me take join between these 2-3 tables. And then it used to, and these queries were optimized in a way that we were taking batch joins. That is, we were not having the join in a way which is done here. So basically, we used to take bulk of things, that let's take data for 10 users from all the tables and then take in-memory join. So we used to optimize things there as well. So we used to make sure that the database is not loaded. And then we used to insert the data in the MongoDB or Cassandra. So when we do that, the computation happens here in this service code. Now, whenever a request comes, we would serve the read API from here, that is the Mongo Cassandra, and the write API would still go there. We used to constantly monitor the lag between the database write and the database read, and you would reach a stage where the lag between write and read would be merely 2 or 3 seconds, or even less than that. So you will reach a point in which you would actually move all the write operation to the MongoDB. So that's how the migration would happen, that you pre-compute everything and then all the write operation initially go to the original DB, but slowly, the moment you have a lesser amount of lag between the original DB and the copy of the DB, you would reach that the things are almost real time. And then you could even migrate the stuffs, or also you could imagine it to be a cache, that you have an ID, the request comes for a particular sale ID, you have everything pre-computed. So if you have everything pre-computed in the form of, Cassandra or something, you can just get the data. And here the replication in the connector used to use something called as Kafka queue. So you could use other things as well, but the idea is not the Kafka queue or anything. The idea is that you pre-compute the responses. So yeah, I think this was helpful, and I hope this was very much clear to you that there are multiple approaches to cache your things. So the first was, of course, around the Redis cache, where you could even have a fallback logic, the thing which we talked about. That was the first one. The second was that we flatten the data and then give the responses by pre-computing. Within that flattening of the responses, there were two approaches. The one was using the materialized view, which is being provided by the database itself. So you don't have to do much, but many times you are restricted by lots of things in your legacy systems. You don't want to burden your database. And there are multiple other things due to which you cannot have a materialized view. In those cases, you put things in a queue, that whenever a new record comes to the database, you run some scripts and make a copy of the pre-computed response to another database, and then you serve the read operation from there. You had to do all those things because there is a system which you could not modify. The best thing would be to modify the database itself, but it's a hard problem to solve. It's not going to happen that today you see a slowness in an API and then you can just redesign the full database, especially if the database is quite old, let's say 10 years, 15 years, or 20 years. In those cases, it just gets hard. And how do you slowly migrate the stuff to the new system, or how do you slowly, first of all, improve the read latency and then the write latency? That's very important. So I hope this video was helpful to you, and I hope the concept of caching and pre-computing of the response was clear to you. That's all from my side for this video. Till the next time, bye.